Whenever we have multiple random variables, it's natural for us to think about the relationships between these random variables. And when we want to start thinking about the relationships between random variables, we need to have different ways of measuring the association that they have. What happens to one random variable as we change another? And probably the most common way to measure the association of random variables is through the use of the covariance. So the covariance between two random variables gives a measure of association between them, and the covariance specifically can be translated into the correlation between random variables. So what is the covariance? Well, suppose that we have two random variables, and we'll call them x and y, and these can represent anything at all. Then the natural inquiry that we're trying to address here is, are there any relationships between x and y? For instance, if we increase the value of x, do we expect there to be a change in the value of y? Should y also increase? Is y going to maybe decrease, right? Maybe y stays the same. Maybe there is no relationship there. So wondering what happens to y as we change x. So for instance, if x represented the number of hours that you study and y represents your score on an exam, you would expect that as x increases, so too would y. If you increase the number of hours that you're studying, then you should also be increasing the score that you get on an exam. If x were to measure the number of potholes on a road and y measures the speed of a car, then we might actually expect there to be a negative relationship between these two, right? If x increases, there are more potholes on the road, then perhaps drivers are going to slow down while driving on that road, right? And so then as a result, we would have there being a negative relationship. As the number of potholes increases, the speed of a car is going to decrease. Now, if x were to measure something like the month or the day of the month that someone is born on, and y measures their height, then we probably expect there to be no relationship between these two variables, right? The day you're born on throughout the month probably doesn't have a meaningful impact on the height that you have, and they're probably not associated with each other in any way. Knowing one doesn't really tell us anything about the other, and as a result, we would expect there to be no association. Okay? The covariance specifically, if we wanted to calculate it, is going to be given to us by this expression here. So, namely, it's the expected value of x minus its mean times by y minus its mean. Now, if we want to actually calculate this, there's a shortcut formula for calculating this. So that's the expected value of x times y minus the expected value of x times the expected value of y. And the thing that should jump out to us looking at this formula is that it's quite similar to the formula for variance, right? What we have here is x minus its mean, right? And then we have y minus its mean, and we multiply those two things together, okay? And that's sort of the terms that we're thinking about with the variance itself, which is where the idea of this covariance is coming in. But it turns out that this is going to actually be a measure of linear association between two variables. It's going to tell us how well does a straight line actually capture the impact of one variable on the other, okay? The expectation here is taken with respect to the joint distribution of x and y. So when we think about this expectation here, notice that we have two random variables in it, right? We have x and we have y. Those are both random quantities. And as a result, we need to be thinking about this expectation with respect to our joint distribution rather than to the marginal distributions. Now, if we calculate the covariance, it's worth us sort of studying what the properties of the covariance will actually be. And so an important note is that the covariance can actually be either positive or negative. Our variances are always positive, but covariances are going to be either positive or negative. If it's positive, then we say that the random variables are going to move together. Increasing one indicates that there's going to be an increase in the other on average. If it's negative, then the opposite is true. So if we increase one, the other one should decrease, and vice versa. Okay, if it's 0, which is possible, then we expect there to be no linear association. Increasing one does not linearly change the other. The covariance is also symmetric, and so by that we mean that the covariance between x and y is the same as the covariance between y and x. Right? We just swap the order that we would be calculating them in. The covariance of a random variable with itself actually gives us back the variance. And so that's to say that the variance of x is equal to the covariance between x and x. And if we think about the definition of the covariance, right, that's going to be the expected value of x minus its mean, right? And if we want the covariance of x with x, then we'd also multiply x minus its mean, right? And if we simplify down, what is that? Well, that is just the expected value of x minus its mean squared, which is our variance. Okay, and so this follows directly from the definitions here. But so if you take the covariance with a random variable and itself, you're actually just calculating the variance. Okay. Now, the linear transformations of random variables are also going to pass through our covariance. And so what we mean by that is that if you want to take the covariance between ax plus b and cy plus d, right, then this is going to give us a times c times the covariance between x and y, right? So we have the expression here, and the constant multiples, right, a times x and c times y both come out front, okay? And then the constant additive terms, plus b and plus d, are actually going to just be dropped, right? Again, this is similar to the behavior of the variance, where constant addition doesn't actually change our variability, but multiplication does actually multiply. Okay. Now, importantly, the covariance does not measure causality, right? So we often talk about what happens to one variable when another one changes, but this does not have to mean that things are causally related, right? You might think about, for instance, the rate of crime that's happening, and you might think about the amount of ice cream that is being sold. And those two are not causally related to one another. As you sell more ice cream, that's not going to cause people to do more crime, and people doing more crime does not cause there to be more ice cream sold. But it turns out that both of these are going to be positively related to one another. They'll have a covariance that is above 0. And why is this? Well, both of them happen to be related to a third variable, which is the season. In the summer, there is more crime that is committed, and in the summer, there's more ice cream that is being sold, right? And so you can have these situations that come up where we have a positive covariance, a covariance greater than 0, that has no causal effect. And so importantly, our covariance is not measuring causation. Another critical point is that covariance does not measure independence, right? If you have a covariance of 0, that does not mean that the two variables are independent. And the reason for this is because covariance is a measure of the linear association. So we're basically asking, is there a straight line that we can draw that predicts one variable from another? Can we say that as one increases, the other one increases, and it's going to increase by some linear factor, right? So if you increase the one even more, it will increase the other one even more. Okay, and so if we have a positive covariance, then we'll have a positive straight line that connects these variables. If we have a negative covariance, we'll have a negative straight line that connects these variables. And if we have 0 covariance, it means there is no straight line that is going to be connecting these variables very well. There might be other types of lines that are not straight lines that do, but there is not going to be a straight line that does. Okay. The other important piece of the covariance is that it is unscaled, right? The actual value of the covariance does not mean a whole lot to us, at least not without context. So a covariance of 10 is not necessarily a stronger relationship than a covariance of 1. It's going to depend on the underlying variables there. So let's look at some examples, right? Here we have x and y, and they're given their joint distribution function in a table here. And we want to know first, what is the expected value of x, right? So for the expected value of x, we're going to want to take each of the values of x times by the probability it equals that value. And if we want the probabilities, then we can add up the individual probabilities in the joint distribution here, right? So the probability that x is equal to 1 is going to be 0.3 plus 0.05, for 2, 0.1 times 0.05, and then for 3, 0.1 times by 0.4. And for each of those, we're going to multiply it by the corresponding value here, right? So if we actually write that down, the expected value of x is going to be 1 times by the sum of the two probabilities, plus 2 times the sum of those probabilities, plus 3 times the sum of those probabilities, and doing that works out to be 2.15. Okay, so the expected value of x here is 2.15. What about the expected value of y? Well, with the expected value of y, we can do the same thing, except instead of us looking at columns, we are now looking at rows. Okay, so we're going to have 1 times by 0.3 plus 0.1 plus 0.1, and then we're going to have 2 times by 0.05 plus 0.05 plus 0.4, right? And so if we work that out, expected value of y is 1 times by its probability plus 2 times its probability, which gives us 1.5. Okay. So what is the expected value of x times y? So for this one, we go through the entire joint distribution, right? And we take x times y times by the probability. and then x times y times its probability, x times y times its probability, and so forth, right? Through all of the different combinations here. And then once we have done all of the different combinations, we add those all up, and that's going to give us our joint expected value. So we take 1 times 0.3, 1 times 2 times 0.05, 2 times 1 times 0.1, 2 times 2 times 0.05, 3 times 1 times 0.1, and 3 times 2 times 0.4. And doing all of that gives us 3.5. Right? So now we have the expected value of x times y, the expected value of x, and the expected value of y. And so naturally, we want to find what is the covariance here, right? Where we've broken this down into each of the individual parts, because the covariance is going to be given to us by the expected value of x times y minus the expected value of x times by the expected value of y. And so in our case here, just using the results from A, B, and C, we get 3.5 minus expected value of x is 2.15 times 1.5. And so then working that out will give us our covariance here. Okay. And so if we calculate that, we get a covariance of 0.275. And so there is a positive linear relationship between these two variables. And if we think about what's going on here, this probably should make some sense, right? If we look at where is there high probability, right? There's high probability in this 0.3 and in this 0.4 terms. And what is happening there? Well, in the 0.3, x is at its lowest value and y is at its lowest value. And in the 0.4, x is at its highest value and y is at its highest value, right? And so what we're sort of saying there is that if we think about sort of plotting out the likely values that we're going to see, then when y is low, it's likely that x is also low. And if x is high, it's likely that y is also high, right? So we have this positive linear relationship here, okay? It is, of course, possible that when y is low, x is actually going to be high, but this happens with lower probability than this does, okay? And so if we think about sort of the probabilities there, that's what we're envisioning. Okay. Now, with the covariance, because it's an unscaled measure, we don't actually know how strong the relationship is without further context. And in order to address this, we can introduce the correlation, and specifically Pearson's correlation. So what is the correlation? Well, the correlation is going to be a standardized version of our covariance. And so the covariance arises in many situations. However, if we do not know the details of these random variables, then the covariance does not give an interpretable measure of the magnitude of the linear relationship. With us saying 0.275 on the previous example, we don't know, is that strong, is that weak, without knowing more about the random variables. And the correlation attempts to address this concern. Okay? So with the covariance, we can only interpret meaning if we also know individual variances. As a result, what we can do is we can introduce the correlation between two random variables. And the correlation, which we denote using the letter rho, the Greek letter rho, is going to be defined to be the covariance between two random variables divided by their individual standard deviations. Okay, so the covariance of x and y divided by the standard deviation of x times the standard deviation of y. And what it's going to turn out is that this correlation now becomes a standardized measure. And so in particular, the correlation or Pearson's correlation or the correlation coefficient, all of these words refer to the same term, is going to be such that it always falls between -1 and +1. Okay? The closer it is to -1, the stronger the negative relationship. The closer it is to +1, the stronger the positive relationship. The closer it is to 0, the weaker the relationship is in general. Okay, and so now, with the size of the correlation, we know something about the relationship that we would not have known if we had only seen the covariance. Okay, so if x and y are perfectly positively correlated, then the correlation is 1. If they are perfectly inversely correlated or negatively correlated, then the correlation would be equal to -1. If they have no correlation being 0, then rho is going to be 0. Okay? And so with the correlation, the main benefit that we get is that we don't need to know the standard deviations or the variances of our random variables in order to interpret the magnitude of the effect here. And that's because it incorporates those variances or those standard deviations implicitly. Okay? So looking at some examples, take x and y to be random variables such that the expected value of x is 3, the expected value of y is 2, and their joint expected value, x times y, is 4. The variance of x is 9, and the variance of y is 4. So first, what is the covariance between x and y? And so recall that the covariance is always going to be given to us by the expected value of x times y minus the expected value of x times by the expected value of y. So the expected value of x times y is 4, right? The expected value of x is 3, the expected value of y is 2, and so then we get 4 minus 6 to give us negative 2. Okay? And so we have a covariance of negative 2. Now, what is the correlation between x and y? Right? And so the correlation between x and y, which we could write down as rho with a sub xy if we wanted to, is going to be the covariance between x and y divided by their individual standard deviations. Okay. We found that the covariance in the first part is negative 2, and the standard deviations are going to be given to us by the square roots of the variances, right? So it's going to be the square root of 9 and then the square root of 4. And so that's going to be negative 2 divided by 3 times by 2. So that's negative 2 over 6, which is negative 1 over 3. Okay, and so we have a negative correlation here, and it's a moderate negative correlation, right? It's not as strong as it can be, but negative 1 over 3 is going to be sort of a moderate value. So again, to calculate out our correlation, we take the covariance as negative 2, take negative 2 divided by the square root of 9 times the square root of 4, that's negative 1 over 3, and that's our correlation here. And what is the correlation coefficient? How can we interpret that? Well, because it's a negative value, we know that there's a negative linear relationship between these two quantities, and 1/3 is a moderate value, right? And so considering the linear relationship between x and y, we expect that overall there is a negative trend, and it's a moderately strong negative trend. Okay, let's look at another example here. Suppose that rho is 0.5, so our correlation is 0.5. The variance of x is 16, and the variance of y is 25. What is the covariance between x and y? Okay, and so in this case, right, we are trying to actually back solve for our covariance here. We know that the correlation is going to be 0.5, which we also know is given to us by the covariance divided by our standard deviations. Right, and so if we want to get to the covariance out of this, then we can take rho times the standard deviation of x times the standard deviation of y. Right, and doing this is going to allow us to solve for our covariance here, and so then we can plug in all of the values that we know into those terms. Okay. And doing this is going to result in us saying that rho is going to be 0.5 times the square root of 16 times the square root of 25, which gives us 10. So the covariance here is 10. Now, suppose that we have a covariance of 100. Standard deviations both are 50. What is going to be the value of the correlation? Well, again, our correlation is the covariance divided by the product of the two standard deviations. And so in this case, that's 100 divided by 50 times 50. Right? And so if we actually work that out, we get a correlation of 0.04. For part C, is the linear relationship that is described in A or B stronger, and why? Okay, and so the important thing for us to think about here, right, is that if we looked at the covariance of both of them, the covariance in A is 10 and in B is 100. Okay, and so if we're just looking at the covariance, well, it's going to seem like the covariance from part B is larger, right? So that's perhaps implying a stronger relationship. However, we have to remember that the covariance is unscaled. And so instead, we could look to the correlations, okay? And the correlation in B is only 0.04, whereas the correlation in A is 0.5. And the correlation gives us a standardized measure. And so higher correlations indicate stronger linear relationships. And as a result, the relationship explained in part A is actually a stronger linear relationship than the one explained in part B, right? So even though the covariance is higher, the linear relationship is not as strong. Right, and this is because the covariance is only interpretable with respect to the actual variances as well. In part B, the variances are very high, right? Standard deviations of 50, whereas in part A, the variances are fairly low. So it's going to be a standard deviation of 4 and 5. Okay, so as a result, the linear relationship in A is stronger. Now, if we're wanting to sort of have a sense of what do these relationships look like, we could imagine drawing data points out of a perfect sort of representation of our population distributions. And so the idea here is in this plot, we're looking at different values for our possible correlations, okay? And so in this top chart, we're sort of thinking about what would the data sets look like where we're plotting y along our y-axis and x along our x-axis if we were taking random samples of our data. And this top plot sort of shows us the idealized setting in a lot of ways, right? So with a correlation of 1, we're thinking that it's, this perfect straight line between them, right? A 0.8 is going to be a weaker straight line, 0.4 weaker still, 0, there's sort of no straight line, negative 0.4 is going to be a fairly weak one, negative 0.8 is a fairly stronger one, and negative 1 gives us this perfect negative relationship, right? And so that's sort of the idea that we're thinking about with our correlations here. However, it's important for us to also recognize that a straight line does not have to be a steep straight line, right? If it's going to be a straight line and everything falls perfectly on that straight line, pointing up, it's always going to be a perfect 1 correlation. And same thing going down, it's always going to be a perfect negative 1 correlation, right? So if there's perfect relationship, then it's either going to be a positive 1 or a negative 1, no matter what. Now, in all of these other examples here, we end up with a correlation that is actually 0, despite the fact that there are patterns in our data, right? So when we're thinking of 0 correlation, often in our minds, we're thinking of this type of situation right here, where we have sort of a no pattern whatsoever. But in these cases, we actually have patterns. It's just they're not linear patterns, right? So if we think about this one right here, right, we have this sort of parabolic pattern, right? That's going to be a 0 correlation because there's no straight line. If you were to draw a straight line, the straight line that's best is actually just the flat line, right? The same thing's going to go in all of these. There are patterns here, but if we have to draw a straight line through the data, the best straight line is just going to be the straight line directly across, okay? And so importantly, our correlation and our covariance is always going to be a measure of the linear relationship, okay? So if you think about how does this actually generate out, then you can think about, well, what if we draw a bunch of samples from this distribution, and if we're looking at that, then what do we expect the samples to actually look like? If the correlations are 0, it just means that the straight line that we draw is going to be a flat straight line. So the covariance and the correlation each give measures of the linear association between two random variables. The covariance gives an unstandardized measure of this, while the correlation is standardized. This makes it easier to interpret the correlation when it's on its own, but importantly, we have to remember whenever we're interpreting this, these are only linear relationships we're talking about. We can't be using the correlation or the covariance to assess whether more complex relationships actually exist.